In our last class, we defined momentum. It's a physical property of moving objects. We use the letter P. It's a vector quantity, and we get a simple equation, P equals m times v, with units of kilogram meter per second as the unit for momentum. The biggest piece here is momentum is conserved, meaning before collision, the momentum of the system is always equal before and after the collision. And so we can look at any two objects interacting, usually in the form of a collision, and we can calculate their individual momentums and add them up to find the system's momentum. And the momentum of the system is equal to the momentum of the system before and after, right? So you can break down your equation and the number of objects that are colliding. You can add up all the momentum on one side. Then after the collision, we look at the momentum on the other. The key here is you can actually ignore all these external forces like friction, gravity, air resistance, simply by assessing what is happening at the instant before the collision and the instant after, where gravity and friction and air resistance wouldn't have a chance to take effect to change those velocities. So as long as you don't add or remove any mass, and we define that system, then momentum is always conserved. All right, so we collided a couple carts, we set up our equation, make sure you're careful with the signs, and we can determine the velocities after a collision. And we looked at this second kind of equation, or collision, where you had the carts stick together. And we took it a step further and started to look at, well, what's happening with energy? And we were able to look at the kinetic energy of the system before and the kinetic energy of the system after. Right? In this collision where they stuck together, we saw that we lost some energy, typically due to heat, when these cars collided. So I want to pick up right where we left off here and talk a little bit more specifically about these different types of collisions. With momentum, we have two basic types of collisions. The first we call elastic. So an elastic collision is defined as one where the kinetic energy is conserved. Ke is conserved. Pen's being a little funky here. Which simply means that if I look at the system or the objects interacting, typically it's going to be two things colliding. The kinetic energy of that system before the collision, initially, is therefore equal to the kinetic energy of the system after the collision. All right, so we're looking at a collision. If it's elastic, that's an easy way to think it. They're bouncing, and you think of bouncy ball or billiard balls, things are elastic. But that defines specifically a situation where kinetic energy is conserved. Now, momentum is always conserved, so you could also say that the momentum of the system at the beginning is equal to the momentum of the system at the end, right? So that's going to be true regardless of your type of collision. And when you get to more advanced physics, you'll see that you can actually use these two equations as a system of equations to solve for specific cases where we have elastic collisions. Now, the reality is elastic collisions would be one where you lose no energy in the collision, which if you think about how a collision is going to occur, you're going to hear the collision. You might have some damage, some dents when those things collide. All these things are friction and therefore lost energy when that collision occurs. So it's important to understand that in the real world, an elastic collision is very rare. You would have to have a collision where there is no sound produced, and all that kinetic energy is therefore restored after that collision. Right? It would require no friction or vibration. However, from a physics standpoint, we might decide to define an elastic collision in a problem and use this conservation of energy to help solve it. So some collisions do come close. To being considered elastic. When we collided those Newton's cradle steel balls, those are very, very close to being in an elastic collision. The balls almost return to the same height that you drop it. So Newton's cradle would be a good example of a nearly elastic collision. Billiard balls on a pool table. And other really bouncy things like, maybe a golf ball right? And there are others that are close. The reality is almost every collision is going to lose some kinetic energy, and therefore will fall under the category of something that is not bouncy, or rather inelastic, which is our other main type of collision. And inelastic, if elastic is defined as kinetic energy being conserved, then inelastic would imply that kinetic energy is not conserved. We lose kinetic energy. And typically that energy is lost to the form of thermal energy. Remember, energy is also conserved if you consider the bigger system. And the problem is when you have a collision and you lose it to heat, that heat is going to the atmosphere, to the air around, and it's hard to capture that heat again. So it's often referred to as being lost. That mechanical energy of the motion of the objects, you lose that mechanical energy to a different type of energy of heat. So we'd say that we lost some kinetic energy. And as a result of that collision, you're typically going to see some deformation or change of shape of the object. You might have a dent when you have this inelastic collision. So it'll typically deform or change shape due to that collision. Now there's a special kind of inelastic collision, and we actually did an example problem like that the other day, where the objects collide, they lose a ton of energy, and in fact they stick together after the collision. And that's a special case. We call that a perfectly or completely inelastic collision. It's so inelastic that it doesn't bounce at all. It's perfectly inelastic or completely inelastic collisions, right? And so these are defined as the objects sticking together and moving together as one after the collision. So the objects stick together. Oops, on my notes. They stick together and move with the same velocity. So you might see a problem that say, hey, the two cars collide inelastically, or more specifically, they collide perfectly inelastically. And you would know that, well, then after that collision, they must be stuck together. And what's nice about that is we have our same momentum equation, right? The first object's mass and velocity at the start, the second object's mass and velocity at the start. But because they stick together, the two masses combine into one mass moving at one final velocity. So you no longer have two different velocities, you have one final velocity. Now, if you were to distribute v final in there, you would see that it's our same original equation that we've been doing for momentum. But we see that really you have this combined mass, and the algebra plays out such that you can group it, and the equation actually looks like what happens in the collision. The two different masses become one mass, right? And there's a lot of examples where you see a perfectly or completely inelastic collision. Anytime you catch a ball, the ball and the person catching it become one thing moving together. If that person was standing on ice and you threw a med ball at them, that person would slide backwards due to that collision. In football, you might have a form tackle where they grab onto the opponent and take them to the ground, right? That would be a form of an inelastic collision, a perfectly inelastic collision. Now, you could have other types of tackles where they drive their shoulder and they don't grab on and they finish apart. That would also be inelastic, but it would not be perfectly or completely inelastic. You even have some scenarios where objects start together and then they finish apart. Maybe the non-scientific way to describe this, but a very visual way would be to call this an explosion, where we have a completely inelastic collision in reverse. A good example of one of these would be, unlike catching a ball where a ball is thrown and caught and the two objects move together, well, we could throw a ball and the ball and the person would be separate after that interaction. We could fire a gun and that bullet that is in the gun is no longer in the gun. It's moving in velocity. It now has velocity. And of course, after you fire that bullet, the gun has some kick because the gun itself has gained velocity in the other direction. Right? And so you might see that those two objects, mass 1 plus mass 2, moving at some initial velocity. Oftentimes that's at rest or 0. Well, then later, that first object would have its own velocity, and the second object would now be moving with some final velocity. Right, so you see there's some different variations of that same equation that we've seen, but these are for specific cases where you have a perfectly or completely inelastic collision. So I just want to walk through real quick an example of one of these types of collisions and kind of show you how you might calculate this. So, if we have our marble launcher that's spring-loaded, and we were to put it on a cart on a track so that we can have no friction, right? I'm going to draw a picture here. There's our launcher. It's spring-loaded. You got the ball in here, right? And that launcher this time, instead of being on the ground, is on some wheels, right? And this would be before it's launched. We'll call that our initial situation. And you might know that the ball itself has some mass. Let's call it 15 grams. And the launcher has its own mass. Let's call that 1,000 grams. Well, later, after you fire it, that same launcher, well, now that ball has left the launcher. At the instant after, we have some velocity. And let's say that the ball is moving at 5 meters per second. Well, what's happening to the actual launcher? Well, if momentum's conserved and there was no velocity before, well, then we should have a little bit of velocity at the end moving to the left. Right? And so we can set up an equation here to figure out what that velocity would have to be. Right? And just as before, since momentum is conserved, the momentum of the system at the start has to equal the momentum of the system at the end. Well, what is that system? Well, before the collision, it's the combined mass of the ball and the launcher moving with some initial velocity. And later, it's the mass of the ball moving with its velocity now as it's left the bezel, plus the mass of the launcher with its own now velocity at the end, which would be that kick backwards. And we can simply sub in the values here. Now, be careful because 15 grams, we're going to want to make sure we put that in kilograms, 0.015 kilograms. And 1,000 grams is just 1 kilogram. Right? We always want to be meters, kilograms, and seconds. But I can plug in the values I know. So if I add 0.015 to 1, I get 1.015 kilograms of mass. Well, it's not moving when you fire it, so I get to put a 0 right here, 0 meters per second. So I have no momentum at the start. Well, then my right side better add up to 0 as well. Well, I have the mass of the ball, 0.015, times its velocity. It's moving to the right. I make sure I put my sign with it, positive 5, plus the launcher's mass of 1 times the launcher's final velocity. And so as you see, you got an equation with only one unknown. When I multiply those things out, I get the momentum of the ball is 0.075, and I have a launcher with a final velocity. And so when I solve, I find that the launcher's final velocity is to the left at a very small amount of velocity. right? The ball's moving at 5 meters per second. The launcher is moving to the left, the other direction, at 0.075 meters per second, which would make sense, right? That launcher is a lot heavier. This is why cannons are really massive, because it's firing a heavy cannonball, and the more massive the actual cannon, the less it's going to accelerate due to that force, right? This is all tied into Newton's third law as well. There's a force on that ball fired out of this launcher. Well, that same force goes back on the launcher. However, that launcher is more massive, so it accelerates less, and therefore that velocity after the collision is just 0.075. Right, so there's a good example of a completely inelastic collision, in this case in reverse. If that ball were to strike the launcher and enter the launcher, you would find that they would move together as well, and that would be your more typical completely inelastic collision.